Physicists at CERN, the European Organisation for Nuclear Research, have refined their understanding of the mass of the W boson, finding it to be some 80,360 megaelectron volts. In physics, an electron volt is a basic unit of particle energy, the amount of energy gained or lost by a single electron as it accelerates from rest through an electrical potential difference of 1 volt in a vacuum. It equates to about 1.602 by 10 to the minus 19 joule. The energy of visible light ranges from about 2 to 3 electron volts. And thanks to Albert Einstein's famous mass-energy equivalence equation, E equals mc squared, or energy equals mass times the speed of light squared, it's also a unit of mass in physics and astronomy, giving 5.6 times 10 to the 35 electron volts to the kilogram. The W boson is one of 30 fundamental particles that make up the standard model of particle physics, the foundation stone upon which our whole understanding of the universe is based. W boson is a gauge boson. It's a force particle, and it carries the weak nuclear force, which is responsible for the beta decay of particles and nuclei, a form of radioactivity, and which initiates the nuclear fusion reactions that power the Sun. The weak nuclear force is one of the 4 fundamental forces of nature, the others being the strong nuclear force, which is mediated by the Z boson and works inside the nucleus of atoms, where it keeps photons and neutrons together with each other. Then there's the electromagnetic force, which is moderated by the photon and transfers energy, such as electricity, light, and heat. And there's the gravitational force, which may simply be the effect of mass bending the fabric of space-time. Physicists refer to the yet-to-be-discovered graviton as the potential mediating particle for the gravitational force. The new, more precise measurement for the mass of the W boson was derived by a scientist with the ATLAS experiment, one of 4 major particle detectors around the Large Hadron Collider, the world's largest atom smasher, a 27-kilometre-long ring located 100 metres underground along the Franco-Swiss border near Geneva. The preliminary findings are based on a reanalysis of some 14 million W boson candidates produced in proton-proton collisions at the Large Hadron Collider. The new measurement concurs with and is more precise than all previous W mass measurements except one, the latest measurement from the CDF experiment at Fermilab's Tevatron accelerator. The W boson's discovery at CERN 40 years ago helped confirm the theory of the electro-weak interaction, which unifies electromagnetic and the weak nuclear forces. That theory is now a cornerstone of the standard model of particle physics. The CERN researchers who enabled that discovery were awarded the 1984 Nobel Prize in Physics. Since then, experiments at particle colliders at CERN and elsewhere have been measuring the W boson's mass with ever-increasing precision. See, in the standard model, the W boson's mass is closely related to the strength of the electro-weak interactions and the masses of the heaviest fundamental particles, including the Z boson, as well as the top quark and the Higgs boson. In this theory, the particles constrained to weigh some 80,354 million electron volts with an uncertainty of just 7 megaelectron volts. Any deviation from the measured mass from the standard model prediction would be an indicator of new physics, possibly new particles or interactions. To be sensitive to such deviations, mass measurements need to be extremely precise. In 2017, ATLAS released its first measurement of the W boson's mass, which was determined using a sample of W bosons recorded at ATLAS in 2011 when the Large Hadron Collider was running at a collision energy of just 7 tera-electron volts. It's now doing double that. Back then, the W boson's mass turned out to be 80,370 megaelectron volts, with an uncertainty of 19 megaelectron volts. Now, at that time, this result represented the most precise W boson mass value ever obtained in a single experiment, and it was in good agreement with the standard model prediction and all previous experimental results, including those from experiments at the Large Electron Positron Collider, the Large Hadron Collider's predecessor at CERN. Then last year, the CDF collaboration at Fermilab announced an even more precise measurement based on an analysis of a full dataset collected by the Tevatron. That result measured the W boson at 80,434 megaelectron volts, with an uncertainty of 9 megaelectron volts, which differs significantly from the standard model prediction and from other experimental results. And it was that which called for more measurements to try and identify the cause of the difference. Now, in this new study, Atlas reanalyzed the 2011 sample of W bosons, improving the precision of its previous measurement. The new W boson mass of 80,360 megaelectron volts with an uncertainty of 16 megaelectron volts is 10 megaelectron volts lower than the previous Atlas result and 16% more precise. Importantly, this result is in agreement with the standard model. In addition, Atlas also verified the theoretical description of the W boson production process using dedicated Large Hadron Collider proton-proton runs. Due to an undetected neutrino in the particle's decay, the W mass measurement is among the most challenging precision measurements performed at Hadron Colliders. It requires extremely accurate calibration of the measured particle's energies and momenta, and a careful assessment and excellent control of the modelling uncertainties. Atlas physics coordinator Pamela Ferrari says further measurements of the W boson's mass are expected from Atlas, as well as CMS and the L8CB detectors on the Large Hadron Collider, the L8CB having already weighed the boson in the past.
W boson is a fundamental parameter of the standard model. And as such, if we measure something that slightly differs with respect to what the standard model predicts, this will be a hint of new physics. What we have done is that we have reanalyzed our data and we managed to reach a much better precision. So initially we had a 19 MeV precision and now we have a 16 MeV precision on the W mass. This actually accounts for a 16% improvement on this difficult quantity to measure. So every percent of improvement, it's really, really difficult to reach. The comparison with respect to previous measurements confirms us that our measurements are in agreement with the standard model. How did we obtain that? We obtained it by improving our analysis methods, so decreasing the systematic errors that we had on the measurement. Then we used a better knowledge of the modeling of the production process of the W and of the substructure of the proton. Of course, this is not the end of the story. We hope, and we will, use new data that haven't been analyzed to investigate this further. So this is still an open quest, and the future will tell us more.
That's Atlas Physics Coordinator Pamela Ferrari, and this is Space Time.